Hello, everyone, and welcome to our today's webinar with Dr. Yucelen from University of South Florida, who will talk about the research in his lab. My name is Zuzana Fabushova, and together with my colleague, Pasha Javid, we will be your hosts and webinar moderators today. And now I will pass the microphone to Pasha to introduce Dr. Yucelen.
Thank you very much, Susanna. Hello, everybody. Good morning or good afternoon, depending on where you're joining us from. Thank you very much for being here. My name is Pasha, and I look after our academic clients across Americas, and I've been given the pleasure of introducing today's presenter, who I have known for about 8 years now. I've had the pleasure of knowing Tansel since his days at Georgia Tech, his final weeks at Georgia Tech before his move to Missouri University of Science and Technology, where we continued collaborating up until today, where he is at the University of South Florida. So Tansel received his PhD in aerospace engineering from Georgia Institute of Technology. Prior to joining USF, he held an assistant professor position at Missouri University of Science and Technology, as well as a research engineer position at Georgia Tech. His research is focused on dynamical systems and controls with specific interest in adaptive and robust control of safety-critical systems, distributed estimation and control of networked multi-agent systems, resilient and secure robotics, autonomous vehicles, and cyber-physical systems, as well as biologically inspired, complex, large-scale, and modular systems. He's co-authored more than 200 peer-reviewed papers in top internationally recognized journals and conferences, and secured external grants and contracts through NSF, Air Force Research Lab, Air Force Office of Scientific Research, Army Research Office, DARPA, MDA, NASA, and more. He's a member of the National Academy of Inventors, a senior member of the AIAA, and a senior member of the IEEE. Without any further ado, it's my pleasure to pass it on from Toronto to Tampa and to our good friend, Professor Tansel Yucelen.
Thanks a lot, Pasha. First of all, again, for the entire Quanser team, Zuzana and Pasha, thanks so much for the invitation. All right, first, I would like to start with a background, and in the meantime, you will see some pictures that I took. This is from Florida, Florida Keys. All right, so Pasha covered most of the details here. All I can add is, in addition to getting PhD from Georgia Tech and then being assistant professor here at Missouri S&T, I also did consultant to NASA, Wichita State and Missouri, and I was a summer faculty fellow at AFRL, RQ at RW. Here, I am directing Laboratory for Autonomy, Control, Information and Systems, which is funded by the agencies Pasha mentioned, where we focus on discovery of novel control, information, and decision systems. Right now, we have 7 PhD students. In the past, we had 5 PhD students graduated in top places, and 3 master's students graduated as well. And we are also directing, similar to Quanser's webinar series, 4th series, forum on robotics control engineering at DSF with the below link. All right, so I would like to start with a video which will provide a general overview of the research topics that we do in my lab. So, for example, the first one is in collaboration with NASA, a flight test. I can mute. So basically, we work on robust adaptive systems, mostly for aerial applications, such that you can see plots like this. On the above plot, for example, you have a pitch rate, the nominal controller of the aircraft from real experimental flight, not able to track the pitch rate command, which is the red line. And when we turn on the adaptation learning mechanisms, basically we can track it well. Let me turn back to the video. You can see the sinusoidal type of command you can track well. Roll rate, nominal controller above cannot track. When we turn on the adaptation, we can track it better. Or we have cases like this. We insert time delay, for example, then we turn on the adaptation on Georgia Tech Airstar vehicle, then it tracks well. This is a video from my lab. So basically, this multi-agent system subject to these disturbances generated from these turbines, blue. How we can develop, robotic swarms in a robust fashion, such that here they are encircling an environment, or how we can deploy vehicles from ground robots, such that they can create a formation, they can do some tasks, so on and so forth. So this is the second theme in my lab, robotic swarms, in addition to robust adaptive systems. Another swarm example with 10 vehicles, they are sweeping formation. Path planning, guidance, type of design, control design. Here, the third theme of my lab is human system interactions. Here is the Tyler. Right now, he is at Lockheed Martin. So basically, Tyler from the watch, applying commands to this four vehicle, such that they are going up, down, so on and so forth. And this is another case. In this case, Daniel, my student, is applying commands to the Quanser Qbots. So like Daniel is applying command to this blue car on the left. And then these three Quanser Qbots need to follow this vehicle at the same time. They need to keep the formation and avoid obstacles. Let me turn back to this video. All right, so like this, they are avoiding obstacles while following the car. And the third theme of the lab is dynamic information fusion. So think about a case, from an aircraft, or you are throwing hundreds of sensors to the ground. Above is the original environment, below is the network of sensors that fuses information. So for example, if you look at the bottom figure, you have a bunch of sensors that collaborate with each other. So the idea is how we can reconstruct the original environment, such that if a soldier connects to that environment, she or he will know if there is a threat or not. Let me run the video. So and here, for the sake of the simulation, red corresponds to a threat, blue corresponds to nothing's happening on that environment. You can apply this case to for example, this is a case Daniel created maze. So there are several cameras that fuse information to know where is the position of the ball. And this is a real world experimentation. Again, Daniel is on the picture. So so there are 4 cameras looking at the environment. Only one camera right now sees Daniel. But again, if I am connected to the first camera, although I don't see Daniel, I would like to know the location of Daniel, and I would like to locate, name. I would like to tag if it is Daniel or not. Then, first camera right now sees, and finally, the second camera sees. We fuse information for localization. So that's the fourth theme of the lab, dynamic information fusion. All right, so big picture, a picture from San Francisco. All right, so we in my lab, we work on a lot of problems related with one robot's inner loop. We call it inner loop control design. So when we design a controller, since we deal a lot of mechanical and especially aerospace engineering applications, we would like to have, we would like to handle sensitivity to disturbances. We would like to reject the disturbances. Also, a lot of time we need to deal with modeling uncertainties. You can have a ground robot subject to friction. You can have an inverted pendulum subject to backlash, or different nonlinear uncertainties. You can have a quadcopter subject to wind, or if it is carrying different type of mass, slunk load type of problems. We need to handle these changes in the mass. So we have a lot of modeling uncertainties. Unmodeled dynamics, we have limited actuation. I mean, some of the vehicles are fast, some of the vehicles are slow, so they need to work in together. Outer loop, when time comes to outer loop for swarm type of applications, we often don't have controllability and observability when we look at the system as a network of systems. And we need to control without global information. If you think about, if you have 10,000 vehicles, how you are going to control 10,000 vehicles? You cannot broadcast information. So we need to deal with decentralized or distributed type of architectures. They can collide. We need to handle collisions. They have sensing limitations. If I am close to another vehicle, I can sense, but otherwise I cannot sense. Heterogeneity, I mentioned, the heterogeneity can be due to dynamical heterogeneity. They can have different dynamics. They can have different tasks. And time is another issue. So sometimes for example, guidance type of applications, we would like to finalize some applications at a specific time to increase the element of surprise. So we also need to pay attention to time. And on top of everything, we could have humans, and humans also apply feedback loops. If you think about a simple example, you have a quadcopter, you would like to do roof inspection. You are basically starting from the ground. You, as a human, trying to minimize an error between the, for example, roof and the current position. And once you apply comments, once your quadcopter, goes high to the roof, then you stop. So you are applying, humans apply feedback decisions, and they are subject to muscular decision time delays. They can get tired. So this is another feedback loop. So we, in my lab, dealing with inner loop, outer loop, and human loops. So the overarching aim that for the most methods we are doing is to establish hierarchical control system architectures to allow robotic swarms to accomplish given tasks and under some stability and performance guarantees. All right, so inner loop control-wise, I guess the inner loop is the central of all control designs. So this is a picture from Washington, D.C. All right, so now I will start diving into some details. Inner loop control design, again, we deal with physical systems. They are usually nonlinear. They have time-varying dynamics. They have limited capabilities. They have coupled loops. And for those systems, like everyone else, we do modeling, while we often resort to first principles of physics. We make assumptions. We make model simplifications. Then at the end of the day, most of the models we deal with on the mechanical and aerospace engineering domain, especially, do not adequately capture the physical system. So in that regard, the control objective is to achieve given stability, robustness, and performance guarantees under system uncertainties and physical limitations. And I would like to discuss one more minute about the uncertainty, which is really unavoidable. So we need accurate models, right? Like every control design for establishing control laws, but it acutes to money, and we need labor analysis to do a lot of analysis, a lot of ground flight testing, and it is often very expensive to drive system uncertainties down. So we can look at two extreme examples. Let's look at the first, the left figure, small size robot. So I mean, this is a small size robot which costs around $150, and I don't want to spend a lot of time on modeling this. If I have a tool that can adapt, learn the dynamics, and help me to design a controller, I will prefer that. Or if for high-end vehicles, like on the right, hypersonic vehicle, well, you can spend a lot of money to model hypersonic vehicles, but at the end of the day, you cannot easily ground test those vehicles. They have flexible modes, flexible rigid body type of interactions. So you will, regardless of the fact that how much money you spend, you will have uncertainties. So we use adaptive control methods. And before I introduce adaptive control methods, I would like to pose this question: why not we use fixed gain controllers? Well, certainly there are advantages of fixed gain controllers like robust control methods. Like, for example, linear robust control laws are really elegant. They are fairly complete design techniques. But the thing is, they trade off performance versus uncertainty because they are tuned to a worst case scenario, not to the physical system. In other words, if you look at this graph, I believe you can see my pointer here, mouse. So, if you would like to minimize the performance error for improving the performance, you really need to know the model. Otherwise, if you would like to ensure robustness, your performance will be not that good. On the other hand, adaptive control methods achieve a given performance without excessively relying on models. They can tolerate large disturbances, large system uncertainty levels, and they adapt to the physical system, not to a worst case scenario. They continuously improve the system performance. But there is a problem. They are nonlinear. And like any nonlinear control methods, they are hard to verify because we cannot resort to all nicely established tools like body, root locus, so on and so forth, NIQs. They are hard to verify. So there is a challenge then when time comes to commercialize those adaptive control methods. So here is the punchline. While adaptive control is a promising technology, it's hard to verify. Nature yields to unpredictable transient performance and unknown stable trade-offs due to limited actuation and unmodeled dynamics. All right, so throughout years, we considered a lot of different linear, non-linear dynamical systems. For the sake of this presentation, I would like to focus on this dynamical system, x dot equals to ax plus bu plus d delta. Here, for well-posedness, we need to say the pair AB is controllable. And I am assuming X is available for feedback, full state feedback. If not, well, we have output feedback methods as well. Here, B is parameterized as D multiplied by lambda. And here D is known, lambda is unknown control effectiveness matrix. Capturing, for example, if you have a controller, actuator, if you are flying at different altitudes, for example, its effectiveness will change due to icing, so on and so forth. So this lambda will capture that unknown in the control effectiveness matrix. That's what we call it. And delta, here is the uncertainty, which is parameterized as W transpose multiplied by sigma. W is unknown, sigma is a known basis function, and it captures in this setting matched uncertainties, which often aerospace systems where the controllers are generated through moment actions. So we have matched uncertainties. If not, again, we have methods that deals with unmatched uncertainties. Sigma is known. If not, we have methods. Everyone has methods to deal, to deal with. For example, you can resort to universal approximation tools like neural networks to reconstruct the sigma. But for the sake of this presentation, I'm assuming it is known. We have a reference model. Reference model is nothing but, so you have a dynamical system uncertain, and reference model is nothing but it captures ideal closed-loop system performance. XR is its state, C is the command that we apply from outer loop, and here, of course, reference model should have stable dynamics, so I am assuming AR circuits without loss of any generality, and CT is a bound piecewise continuous command because we often would like to track bounded commands, not unbounded commands. So objective of the model reference adaptive control is that we want dynamical system trajectories X to converge to the reference model trajectories. And once this happens, then our uncertain system will act like the reference model, which is V design. So everything will be good. All right, for this, we often have in any vehicle, if you consider any legacy vehicles in aerospace or mechanical engineering domain, they do have a nominal controller. So often we augment adaptive control signals with existing nominal control signals. And they can be robust controllers as well, optimal controllers, so on and so forth. So here UN is the nominal controller, and you can have PI, PID, different types of nominal controllers. Here, I am assuming, a feed-forward architecture without loss of any generality. So UN is K1X plus K2C. which helps to construct this AR and BR matrix given on the right. And adaptive control signal then is we have x dot equals to when we close the loop with the nominal controller with adaptive adaptation, augmented adaptation. We have x dot equals to ARX, BRC, D lambda, plus as you see from the terms in brackets on the first line. So UA can access to the uncertainty. So I am choosing adaptive controller since W is unknown. We are choosing adaptive controller to be the minus estimate of this uncertainty multiplied by sigma, and W hat dot is a nonlinear weight update law, and that captures this uncertainty. There are a bunch of papers, there are a bunch of excellent books on this topic. I am providing here two references. Here is MRAC, my encyclopedia paper, or you can go to YouTube, Google my name. You can see model reference adaptive control fundamentals, also available at the forum on robotics and control engineering tutorial lecture. All right, so now here is time, for adaptive control, the selection of this omega nonlinear function for the update law is really critical for closed stability and performance. And the standard candidate is given like this, that you can find in almost all textbooks available in model reference adaptive control. You have a gamma adaptation gain. Here is your sigma basis function. X minus XR is the error between your uncertain system state and the reference model state. PD are some matrices, D coming from the dynamics, P coming from the Lyapunov equation. So with this dynamics, really, we cannot assign a user-defined bound to the system error. So here is the idea which is funded by NASA. How we can, while learning, while doing adaptation, how we can preserve a given operational envelope. So you can think like this. So first of all, let's say you put your fancy adaptive controller to an hypersonic vehicle or a passenger plane. During the transient performance, during learning, how do you know a given angle of attack will not exceed prescribed bounds? For example, like in many aerospace vehicles, angle of attack should be limited to, of course, it changes from system to system. Let's say I would like to keep my angle of attack between 5 to -5 degrees while learning. How we can ensure that with adaptive control? Strictly. So existing methods cannot. So for this, we provide some set definitions. For example, let's look at this scalar system showing on this picture. Let's say I design my reference model that operates on this blue region, and XR is the reference model state. I am also defining SF, which is the state space set to describe the operational envelope in terms of robots' states, airspeed, altitude, so on and so forth. In other words, whatever happens, I don't want to exceed SF. So this means that, if you focus on this blue X trajectory, I must learn within this epsilon bound, which is user defined. So during learning, I am not allowed to exceed this epsilon bound. How we can do that? In other words, from a mathematical standpoint, this is the same question. How we can select this learning omega for the weight update law of this nonlinear function such that the system state error evolves in this the epsilon set describing the user-defined error performance bounds. All right. So we have restricted potential function definition, which I am also citing to 3 papers developed by Ehsan Arabi. Right now, he's at, after he graduated, he's at the University of Michigan. So we have this, they are also called generalized Lyapunov barrier functions, depending on which side you are looking at. Let Z of H be Z transpose H Z square root. And here, this is the weighted Euclidean norm of phi, where phi is a restricted potential function defined on a set. If these 5 statements holds, such that if Z is 0, then this restricted potential function phi is 0. If you're on the epsilon domain, then it is positive. if you approach the limit, it approaches the infinity. It is continuously differentiable, and its derivative is with respect to z h to the power of 2 is positive. And here on this figure, you see one restricted potential function candidate satisfying all these 5 conditions. You can find several other candidates. Once you find the one candidate, then you can implement the theory that I am going to show right now. So here on my papers with Ehsan, we choose omega like this. This is the d derivative of the restricted potential function depending on the error, multiplied by sigma x minus xr PD. And we have several different versions of this theorem, but mainly if you start inside your prescribed set, meaning if you recall the example that I gave, angle of attack, if your angle of attack is between 5 to minus 5 degrees, then all closed loop system trajectories are bounded. Error goes to 0, and during the transient time, the difference between x and xr is always upper bounded by epsilon. We do what the standard MRAC does, model reference adaptive controller does. In addition, we guarantee the transient performance to strictly remain on a given operational envelope with this so-called set theoretical adaptive control. All right, so this is an application to the Quanser aero system, and which we would like to regulate yaw angle and pitch angle. On this, you are going to see pitch motor voltage, yaw motor voltage. You are going to see the learning rate and the system error now. All right, so this is the nominal controller, and like any Quanser system, this has very well modeled dynamics. So we are inserting uncertainty to this system such to disturb the nominal behavior. And in this case, basically, you see we have an unstable response due to the uncertainty. All right, so now I would like to stop this video for a second. Here is the epsilon threshold that we assign to the system error norm. During learning, we don't want to violate this system error norm. So yaw angle, we are tracking in this case yaw angle, and pitch rate, we are regulating the pitch rate at the 0 equilibrium point. So as you see, we track the performance. So actual system trajectories follow the reference model trajectories pretty well, and during the learning, we don't exceed this system error norm in the sense that we preserve the operational envelope. All right. That's all I'm going to say about set theoretical adaptive control. It is one of the tools that we develop in the lab for performance. But while developing that, so we also need to pay attention to limited actuation, as I mentioned. Different vehicles have different actuation capabilities. So we really need to answer some fundamental questions, starting from how fast of an actuator do we need to execute our algorithms? Given an actuator, will our system perform as expected, or how is the robustness to the variations in actuator performance? Well, answering these questions fairly easy for linear systems, because we have a lot of design tools. Like, for example, you can look at the body. Like, we have a gain k equals to 11 on this simple unit feedback block diagram. We have a system here, G of S, and we have an actuator dynamic, and we have lambda. Lambda is the actuator bandwidth or time constant 1 over lambda, if you think, depending on how you look at. If it is sufficiently large, then you have a nice stable response with phase margin equals to 45 degrees. If it is 10, phase margin is 18. If it is 1, you don't have a phase margin. Your system starting to become unstable as you decrease more. So we can look at body. Any other method, we simply have a lot of tools for linear systems, so answering those questions are so easy. But if the system is uncertain, or nonlinear systems in general, including adaptive systems, we don't have those tools. So, and there are not much techniques available to analyze limited actuation. Although it is a very simple problem for linear systems, it becomes so hard for nonlinear systems. All right. So to handle the presence of actuator dynamics, like you see here, x dot equals to ax plus b, but not u now, v. V is the output of the actuator that's coming from this xc dot equals to ac xc. So you apply your controller u to this actuator, then output of this actuator drives the system. Now, one can immediately see from this equation, we even cannot cancel uncertainty algebraically, even if it is known, right? Because we now lost in the presence of actuator dynamics, which every system has actuator dynamics. So we lost the chance to algebraically cancel the effect of the uncertainty, because now it is evolving through some dynamics. And we started to look at this problem with mainly with Benjamin, and there are bunch of papers, 4 papers listed below. Right now he's at Army Research Lab in Maryland. So we started to look at with the hedging method developed by Eric Johnson and Tony Caris, my advisor, Tony Caris. It is simply a method. So if you rewrite the x dot dynamics, I put u, I subtracted u, you have a mismatch term b minus u. So if you add reference model dynamics, this mismatch v minus u, subtract from each other, you have the same error dynamics. So this is, again, while originally proposed by Eric Johnson and Tony Caris, so its stability was not proven in the dissertation. And this was the first step that I did with Benjamin under the Air Force Research Laboratory grant and support of Dr. Jonathan Muse. We first established stability conditions, saying that if this A matrix given here is quadratically stable, and we utilize a projection operator, then all closed-loop system trajectories are bounded, and error goes to 0. So this added term to the reference model will not make the reference model state blow up, and everything will stay closed if this quadratically stable condition holds. You can ask the question, well, all right, you are modifying the reference model trajectories. Yes, but we will handle that problem. All right, so then, you know, we have access to a lot of efficient linear matrix inequality algorithms, and we also have the ones developed by us. Basically, you know, we can, for example, if we have an uncertainty with upper bounded by 1, then your actuation can be faster, it can be slower if you look. If your uncertainty is upper bounded by 2, then, you know, your actuation domain, in this case we have 3 actuators, shrinks a little bit to allow fast actuation variations. So we can look at precisely the trade-off between how fast the actuator should be versus how much uncertainty we can tolerate. Before we develop these methods, you know, the existing state of the art relies on it is sufficiently fast such that adaptive controllers can work, but we never knew how fast is fast. But these linear matrix inequality methods allow us to compute how it gives an answer precisely how fast is fast. All right, so unmodeled dynamics, also another topic that that exists in many systems. Again, we can look at 2 examples. One is on the left from NASA picture. So rigid body, flexible body interactions. So and these flexible body interactions create unmodeled dynamics. And here is a slunk load type of an example, swarm slunk load type of an example from my lab. 3 quadcopters carrying mass. And as you see, you know, while they just can't carry simple mass due to this ropes mass, their trajectories are not so precise. While if we fly those vehicles individually, as you saw from the beginning video, they can fly pretty well. But once we add a mass, this added load creates an unmodeled dynamics problem. In general, this is the block diagram, control theoretic block diagram of unmodeled dynamics. So you are applying a control signal. So top you can view as your rigid body system, same system, but now it is affected by the blue part, which is the unmodeled dynamics, for example, flexible body interactions. So the controller you apply, it also goes to that unmodeled dynamics. And output of these unmodeled dynamics also drives your system. So now how we can address this issue? If we destabilize while we can stabilize the up system, if we destabilize the below system unmodeled dynamics, then it will destabilize the upper system. We have a problem, really. We have really, this is a 30-40-year-old problem in the adaptive control literature. We started this method. I work mainly this method with Merve Doğan, Kadriye Merve Doğan. She will be an assistant professor at the Embry-Riddle Aeronautical University starting in August 2020, this year. So basically, we started this problem by looking at a very good paper published by Anu Anaswamy and her students. And then we basically found out that if you consider the standard weight update law, we cannot tolerate large system uncertainties. But this is a problem. Basically, you know, the main purpose of the adaptive control is to handle uncertainties. But, you know, if we have significant unmodeled dynamics, we cannot. So how we, then Merve and I, we were discussing how we can address this problem. So the solution that we have is if you add this corrective signal, mu hat B transpose PE, to the adaptation mechanism, then we still have stability, but we can also tolerate large system uncertainties. All right, so this is one of the experiments that Merve performed on an inverted pendulum. Actually, you know, to create this system, I work with Pasha, and I again thank him a lot. So we have a really nice flexible system that we can readjust, we can adjust these cards, so on and so forth. So basically, if you look at here on the left, you have an inverted pendulum, but now we have this Quanser spring system attached to another card. Card on the right, it is unactuated. It is unmodeled dynamics. We act like we don't know these dynamics. So we are applying adaptive controller to the left one, but we also want robustness to these unmodeled dynamics coming from the right one. So let me play the video. All right, so this is the nominal controller. We have a friction due to, we have an uncertainty due to friction primarily here. So the card goes left and right because of the unmodeled dynamics, because of the friction. At the same time, we are trying to balance, of course, the inverted pendulum. So once again, you know, it is going left and right. Now we are going to turn on the proposed adaptive control algorithm. As you see, we precisely go to that position while having unmodeled dynamics with little oscillation. So we were able to suppress the effect of uncertainties in this case. All right, so basically I discussed several aspects of the inner loop, which happens a lot of physical systems. You know, we do learning, we do adaptation, we would like to rely on prescribed bounds. We would like to know the performance before we initialize the controller for safetyness, for security, so on and so forth. And at the same time, limited actuation, we need to have robustness, limited, you know, the actuation. We need to know how fast is fast. And of course, based on the many applications we perform or people can perform, unmodeled dynamics is an issue. So I discussed these three inner loop challenges. We of course have a bunch of other papers addressing all other issues like disturbances, noise, unmatched uncertainties, using neural networks if you don't know the basis function. I just wanted to give a flavor of what we do in terms of inner loop. Now we are looking at the outer loop. So here's a picture from CDC 2012, if my memory is correct, at Maui, Hawaii. All right, outer loop. Now we have outer loop, we have swarms. Let's say we designed pretty well to control one robot. But now we have a robotic swarm, which can be homogeneous or heterogeneous set of vehicle teams. They communicate with each other in a local fashion. Again, we don't want centralized solutions. They exchange and process local information, and they have robust and scalable nature. Distributed controllers have robust and scalable nature, because if you lose this one vehicle, if you look at the figure, if you lose some connections, one vehicle, still based on the distributed information exchange, the remaining agents can perform the mission. Or you can simply add additional vehicles, as you see from this figure. So it is the same system based on this distributed information exchange. It is really scalable, robust to vehicle losses. So that's why we put a lot of emphasis to distributed control. And control objective is similar to one control objective, similar to sheep herding problem, right? So you would like to drive the robots to specified spatial points in space. We have leaderless algorithms. We have leader follower algorithms like several other authors use. And achieving this objective is easy. It's easy when the overall system swarm is both controllable and observable. Because if it is controllable and observable, if you look at the figure on the right bottom, so there you can view swarm as a networked system, write its dynamics in a similar to x dot equals to ax plus bu. You get output from some of the output agents. You apply inputs to some input agents. So you can steer, you can drive swarm to any spatial position. Since you have control and observability, you can observe the behavior. It is a really easy problem if we have control and observability. But often we don't have. So what can we do? So basically, there are a lot of swarm methods, especially all these methods are popping up much more frequently for the last 2 decades. The problem is once we have higher task complexity, we have harder to control. And in the literature, while multi-agent methods on multi-agent systems getting major and major each year, we really cannot answer simple questions. For example, here is a simple task. You have a quadcopter, 8 robots on this figure, tracking for tracking purposes. Or you have an obstacle, so you would like to send smaller robots to the up, bigger ones to the bottom. And if you need to pass through a bridge, like you see in this figure, you need to scale the formation. Well, existing methods required centralized information exchange. Information broadcasting, so they cannot do this task in a distributed control fashion. So this is the main problem I also would like to emphasize, or maybe give suggestion to other researchers. So on the system theoretic domain, the tasks that we do often are related with consensus formation, containment, coverage, but considering long duration autonomy, we want a scalable system flying outside, I apologize, in a distributed manner. And we need to have the flexibility for that swarm system to do complicated tasks. How we can achieve this? All right, so for example, you can consider simplest formation assignment example. Here, we have 5 agents. We would like to send them to this shape, and we cannot scale because it has a single layer nature. For example, if the radius, if you think about the radius of the shape is 1 meter, and we send those vehicles to those designated positions, after maybe tomorrow I would like to send it to 2 meters or 10 minutes later. So how we can do this? We cannot change the density of the formation due to their single layer nature. So we cannot make complex tasks again in a distributed fashion. So the idea that we developed with Young Tran, right now he's at Air Force Research Lab. He started 2 months ago after he got his PhD. We developed multiplex networks idea. So here is the idea. Well, okay, you have a complicated task. It has different layers. For example, let's say the first is the physical information exchange layer. You see this on the below graph. The second one, let's say we would like to change the density of the swarm. The third layer, let's say we would like to rotate the swarm. So how we can decompose a given complex task into subtasks, assign each layer to each necessary subtasks, and then connect the resulting layers with each other to compose complex motions. How we can do that? And the idea that we got from social sciences and physics community is multiplex networks. And how we can, but now once you have a multiplex network, layered networks having multiple layers, how we can analyze stability and performance. So we find an idea, this requires NIF stability and performance guarantees. Now I would like to give one benchmark example on formation control. Let's say you have layer one. Layer one is the first layer that creates the formation. The second layer scales that formation, which is only available to a leader or a subset of leader agents. So gamma is the scaled parameter. So we diffuse information in the second layer, so which also goes to the first layer, and di is 1 only if this agent is leader. In other words, in this case, we have 2 layers. Only leader knows the formation assignment, and without requiring centralized information exchange, we can make the formation larger or smaller. Young also performed, a bunch of generalizations: leaderless, leader following, collision avoidance, how we can handle sensing limitations, what happens if we have non-identical graph topologies, so on and so forth. All right, so this is the one case that I would like to show, again, with Quanser qbots. So we are tracking this blue car, and the idea is simple. We have this triangular shape to pass through these red bricks. So they need to scale the formation. In this case, if you think about X and Y, we scale the X-axis such that they can pass through this gap. This is with Crazyfly quadcopters. So we have a mission, and we are basically launching the mission. Only the first vehicle here you see is the leader, and only he knows the location of these poles. And first, they change their altitude, as you see here, and they created a path graph. Then, in order to pass through these poles, and this is a 2-minute video, and I am passing it quickly. So they pass through the poles. So the one physical, in addition to the first physical multiplex layer, the second is changes in altitude. Third is scaling the quadcopters in X and Y axis. And then now we are here. We would like to turn back. We would like to rotate the multi-agent system. So we have a rotation matrix only available to leader, and this creates also additional layers, 4th and 5th layers. So we rotate this multi-vehicle system. We again recovered our V shape. And then the mission while turning back is only the leader vehicle need to pass through these poles, and the others need to go from left and right. And leader vehicle applies commands to those vehicles, and everybody distributively going from left and right. And at the end, we recover this V shape again. So this is how we can we can utilize the existing algorithms, take them to the next layer by using multiplex networks to create complex formations. All right. This brings us to time-critical control supported by ARMA Research Lab. So again, as I mentioned, I was doing some faculty fellowship at the Eglin Air Force Base, interacting a lot with my friend Eduardo Paciliao. And one day he mentioned that, well, everything you are doing is asymptotic, which is fine for my case. But if you would like to land for landing problems, or if you have guided projectiles, bunch of small guided projectiles hitting a target, in order to increase the element of surprise, we need to assign time. I would like to hit the target or land in 10 seconds, 15 seconds. So this brought me, and my 2 students were also with me at that time, Yank and Daniel, so at the Air Force. So we started thinking, well, fine, we can probably use existing finite time control approaches to extend our algorithms to do missions in a time critical fashion. Then we found interesting problems. For example, so these finite time control algorithms available in the literature are basically mostly using discontinuous functions, signum functions. And there is a very nice article published in 2000 or 2001 by Dennis Bernstein on that topic. So they guarantee finite time convergence. Again, I am giving a simple example. As t goes to capital T, x goes to 0. But the problem is this finite time constant t is not pre-assigned. It depends on your initial conditions, your controller gain selections. So finite time convergence cannot be a priori assigned. So, but we would like to assign a priori. So here is the idea. Again, there are 4 papers on the bottom basically we consider, for example, idea time transformation. So here is the idea: x dot equals to u in a simple setting, and let C denote its solution over the interval of interest, t0 to capital T. Let T be a strictly increasing time transformation function, such that if you differentiate this, basically you have this phi dot equals to d phi over ds system. So this system and x dot system, they are identical. They are absolutely identical, but they are on different time domains. The first system evolves from t0 to capital T, and when the first system evolves until capital T, the second system evolves until infinity. So under this time transformation, their solutions are all identical, but they are on different time domains. So now here is the idea: once you transform this system to an equivalent system on the infinite time interval, this means the following: you can use all the existing asymptotic methods on the second interval. You don't need to limit yourselves with the existing finite time methods. So for example, consider this dynamics. I am choosing u to be like this, alpha is constant. Then you simply have phi dot equals to minus alpha phi. You know that it is asymptotically stable in the sense of Lyapunov, right? Phi goes to 0 as the new time constant s goes to infinity. But we know that due to time transformation method, once s goes to infinity, T goes to capital T. In other words, you can choose capital T, and based on this time transformation, when T goes to capital T, X goes to 0 for all initial conditions, with capital T being user defined. And if you satisfy this regulativity condition, which is not hard to satisfy, also U goes to 0. In other words, to back up for a second, you can have any system, satisfying specific form. Right now, we are still developing this method for higher order systems. So you have a dynamical system. If you can transform it to the infinite domain, then on that infinite interval, use any controller you like, LQR, PID, achieve some asymptotic properties, transform them back, then you can have prescribed time critical controller with capital T being user defined. All right, so here is the comparison between existing discontinuous like signal function based, for example, finite time methods versus the ones that we develop. The first one is the stabilization case. As you see, we choose, for the sake of this example, finite time to be 0.5. Regardless of the initial condition you start, based on this time transformation method, we always converge to the equilibrium at 0.5 seconds. However, as you see, the standard methods, the blue lines, their convergence time depending on where they start. We have bounded disturbance. You see, regardless of the fact that we have disturbance or not, we again converge at 0.5 seconds. Other methods, the standard method, convergence time changes. Third case is the stabilization with uncertainty. Well, our method is pretty robust to the uncertainty. Again, we precisely have 0.5 seconds of convergence. Existing standard signum-based method can have unstable, stable trajectories. If stable, basically we cannot assign user bound, finite time bound. And the fourth example is command following. Again, we have a command black line that we would like to follow. We would like to hit. So at 0.5 seconds, we are exactly converging to this black line. But existing methods, depending on where you start, it takes time, and we cannot pre-assign the formation. So these are the application to a cooperative swarm engagement. So and for the sake of this example, for experimentation, we would like to. So you have 4 agents on the bottom. You have 2 targets. We would like to converge with the targets exactly at 15 seconds, and duration of this video is also exactly 15 seconds. So we execute the algorithm. So 2 robots on the right needs to engage with the top target, bottom ones need to engage with the bottom one. At the same time, we are converging, and when it is exactly at t equals to 15 seconds, everyone of the swarm member engages with the target. All right, so let me see how I am doing with the time. I believe I have 5 minutes. So this is another research direction, heterogeneous robotic swarm, supported by National Science Foundation. Burak is currently my PhD student, primarily leads that project, and here are several papers published by him. So now, basically, Burak is looking at different problems. One of the first problems we discussed, well, what happens if you have different heterogeneity in dynamics? What happens if some of the agents have local objectives, some of the agents have global objectives? For example, let's say you are flying a swarm. Well, I want some agents to change their batteries, right? So I would like to send them to another location, but I don't want to disconnect from the network as well while doing that. I am only going to give a sense of dynamical example of what Burak does on heterogeneous robotic swarms. So here is harder dynamics. So you have adaptation, xi dot is the uncertain system. You have distributed reference models in this case. And then you have distributed control laws. And one of the ideas we have is if the Zi integrator state has yr of j, this decentralizes the adaptation process, makes the adaptation process decentralized, not centralized. If you really use here yj, everything will be much harder. All right, then we have closed loop swarm stability. If the condition gr infinity or of fa is less than 1, f is here, and a is the adjacency matrix, and the graph has a spanning tree, then everybody yi's output of all agents tracks their output of reference models. So swarm behaves nicely in the presence of uncertainties. And this is an experimental platform again, Quanser's system. Now we have 3 vehicles, 3 carts, one with inverted pendulum, other is right one is small inverted pendulum. The second one has no inverted pendulum. They don't have spring here. They are basically, they exchange distributed information to go left and right. And certainly they have the first and third vehicle has fourth order dynamics, second one has second order dynamics. And this video is performed by, and this experiment is performed by Emre Yildirim. He is currently, he got my master's from me, and he is my PhD student currently, and he is doing awesome work on this type of stuff, and I'm looking at different problems. So, okay, let me run the video. Basically, as you see, they are going, without adaptation, they are going left and right, but again, friction. Because of the friction, you are seeing these basically going. The first and third agents, because they have inverted pendulums, are affected a lot based on this friction. And when we turn on the adaptation, first and third agents basically behave pretty well by following the leader command. All right, so human interactions is the third component of my research. Maybe I can talk more about this later, maybe in a later series at Forset or at Quanser site. So since I don't have time, basically, I would like to show one example. You know, basically because of human decisions, you have time delays, you have a reference model, adaptive controller, uncertain system. Basically, we not only have inner loop, outer loop, but also the dynamics of human. And we develop tools in collaboration with Yildiray Yıldız from Bilkent and Rifat Sipahi from Northeastern, awesome collaborators and awesome friends. So basically, how we can precisely analyze the effect of time delay, effect of human dynamics, what happens in the presence of uncertainties, both at the human side, at the system side. Ahmet Kuru worked on this project as well. Lead this project on when we have multiple agents, and Ahmet is now at Penn State. So how feedback decisions affect the swarm. So, you know, for example, interesting, you know, he developed very interesting architectures and linear matrix inequality based tools on the time domain and on the frequency domain by collaborating with Rifat Spahi and Ramirez. Basically, how different graphs topologies changes the time delay margin. All right, so I passed the human part quickly. Again, if you have any questions, you can let me know. Concluding remarks-wise, robotic swarms, we need a lot of agencies, industries, we are now started to use robotic swarms to address a wide array of social challenges, safety and security. For example, if you think about surveillance and protection of freight passenger convoys, disaster management, transportation, energy, distributed power control, for example, for effective blackout management. These systems are getting there. And to fully understand these systems and reach to their maximum potential, we need to address issues with regard to inner, outer, and human loops. And I presented what I believe is important from my side and my researchers' side. And for hierarchical control architectures, how we can handle disturbances, uncertainties, actuation, unmodeled dynamics, what we can do in the absence of controllability and observability, local information exchange, time-critical jobs, heterogeneity coming from multiple directions, human decisions and multiple time delays toward a unified swarm work. And as this being said, I would like to thank to all my students, first of all, and then to my sponsors, and then Quanser, Zuzana, and Pasha for giving me this opportunity to give my talk on the YOUser webinar.
All right. Thank you very much, Tansel, for the very informative webinar. We certainly look forward to hearing more details about the human loop challenges and your research in a future opportunity. For now, in the interest of time, we do have a few questions. Let's take one, see how it goes. If there are any unanswered questions, we will definitely follow up in written form after the webinar. But for now, the first question is, in time-critical control, if there are hard constraints in the original system, can you handle them in the transport system, in the infinite time domain?
Well, very good question. Answer is yes. Answer is yes. So Ehsan and I, my student that I mentioned, so we developed some stuff before he started his job at University of Michigan, that how we can enforce hard constraints on system trajectories. And after he started with Dimitra Panagao, they published a paper based on the results we developed here, how we can handle control constraints. So right now, I can say for scalar systems, we can do that. But you know, we are really exploring these methods. We have methods for first order systems, second order systems. We are going for higher order systems, and basically it is possible. It is possible, but since we can handle state and control constraints for simple systems, and still, since we are developing those methods for higher order systems, first we need to develop higher order uncontroller methods in finite time for higher order systems, then go with constraint. But the results we have looks like shows that it is possible. Well, very good question.
Thank you, Tansel. We are really a little bit over time, so I don't want to hold our audience for too long. Thanks so much. It was a really great presentation, and we are really open to, continue and give you more space, so you can tell us more about the stuff that you had to go through quickly or skip. Thanks everyone for joining us today. As I mentioned, this presentation is being recorded, so we will give you access to it later, so you can revisit it and even share it with your colleagues. Thanks again, and stay tuned for our next webinar in April.
Oh no, thanks again, everyone, and thanks Zuzana, thanks Pasha, thanks Quanser family. It was a great talk. It was great to give this talk in your forum.
We enjoyed it very much, Tansel. Thanks again, and thanks to everyone who attended. Have a great day, everyone.